Okay, so last week we took a look at NumPy. This week we're going to introduce Pandas, which is a higher level data structure that sort of keeps track of spreadsheet-like information or time series kinds of information, a slightly higher level than NumPy. Okay, so first a quick review. For files, what does the with clause help you with? Choices are, it automatically finds files, it automatically closes files, it enables the W operation so that files are open for writing, it enables the R operation so that files are open for reading. The correct answer here is that by using the with clause, a file will automatically be closed at the conclusion of the with block. So that's a very handy way of not having to worry about whether you remembered to close a file or not. All right, now what must be true if we multiply two endy arrays using the dot method? Do the arrays have to be exactly the same shape? Do the arrays have to be squares? Does the first array's number of rows have to match the second array's number of columns? Does the first array's number of columns have to match the second array's number of rows? Okay, so dot is performing a real matrix-style multiplication of two arrays. And the dimension of an array is given as number of rows by number of columns. So in order to multiply two arrays, the first array's number of columns has to match the second array's number of rows. Okay, you may remember here we were looking at some examples just using using NumPy, and we had this endy array B and this endy array D. And in order to be able to successfully multiply these two things together, the number of rows of... I just said that backwards. The number of columns of the first matrix, which is 4 here for B is 4 by 2, has to match the number of rows of D. D is 4 by 1. So we have 2 by 4 by 4 by 1, and when we multiply those, we get a 2 by 1 result. Okay, so Pandas allows us to do more sophisticated kinds of data analysis. It handles a variety of different kinds of input. We can read information from comma-separated value files, from SQL databases, from Excel spreadsheets. It does support slicing and indexing and subsetting in much the same way that, well, slicing and indexing in much the same way as NumPy, and then subsetting by using what are called Boolean indexes. We can select certain parts of a Pandas data structure that we want to process. And it has oodles of built-in functions for doing things like arithmetic combinations, sorting, and a variety of statistical capabilities. Well, just as we did with NumPy, we're going to have to import the Pandas module in order to use it, and the usual abbreviation for Pandas is PD. Okay, the usual abbreviation for NumPy is NP, and for Pandas is PD. So now that we have imported the Pandas module, we can use facilities in Pandas by saying PD dot and whatever. And if I pause, you'll see that there are a whole bunch of facilities, functions that I can use within the Pandas system. There are two primary data structures for Pandas. The one-dimensional data structure, which is somewhat analogous to the ND array vector, is called a series. And the distinction, really, between an ND array, a one-dimensional ND array in NumPy, versus a Pandas series is that each row has a label associated with it. We don't access we don't have to access the items within a series using integer subscripts like we do in an ND array. Now, we can use integer subscripts. We can also use names or labels that have been given to the values. Series is mostly what we're going to talk about in this lecture. The data frame is a two-dimensional variation on this. Each row has a label, but then there may be multiple columns. Each one of the columns is also going to have a label, a column name, and you can think of the data frame as basically being like a spreadsheet, where you have this two-dimensional collection of values, which may be a combination of integers, floating point numbers, strings, booleans. The data type of each column has to be the same, but different columns can have different data types in much the same way that a spreadsheet does in Excel. Well, a typical spreadsheet, I should say. Okay, so let's take a look first at a series. Now, each item in a series is labeled, and the default labels are the integers from 0 up to 1 less than the length of the series. When you create a series, you can use the index keyword parameter to specify a different kind of index than the default if you would like. So let me show you some examples. I think I'm going to skip over slide 8 here and go on to looking at some specific examples. In this first instance, on the left-hand side, I'm creating a list of values referred to by the variable name data. All right. So, well, data. Let me just copy and paste that and patch up the spelling. All right, so here's data. And to create a series, in a notation that's a little bit like how I would create an array in NumPy, I say pd.series, sort of like np.array, and then I can give my list as the data that I want to have stored in that series. And in my case, the contents of the series is immediately displayed on the screen by default because I neglected to provide a variable name to refer to that series. So let me correct that typo. I'm going to say v gets pd.series of data. All right, so there is v. If I say print v, I'll get the same thing in this case. All right. Now, if I want to get a list out of a series, I can do that with the toList function. So v.toList gives me back a list containing the data within the series. Notice that each one of these items in the series has an index label, which by default, as we said, are just the sequential integers 0 through n-1, where n is the number of values in the series. Okay. So here's data, and that I created the series from. And if I say data 2 gets v.toList, then it's going to be the case that data and data 2 contain equal values. So that's one simple way of creating a series, is to use a list of values as an argument to the series construction function. You can also use an endy array. All right, so let me create X as to refer to an endy array that I'll also create from data. All right, so now X is an endy array. Okay, and I can say v2 gets pd.series x. All right, so Pandas figures out that there's 5 values in this endy array and gives me v2 with the default index values 0 through 4 for the 5 values, and the actual values 5, 9, 10, 12. Now, on my system, I'm getting told that this is an int32. Perhaps on a Mac, you would get int64 by default. I'm not sure. But you'll either get int32 or int64. As opposed to using toList to get a list of values out of the series, it turns out that within the series, the values are stored as an attribute in much the same way. Okay, let me back up a little bit. If I say x dot shape, I knew I would think of it. If I say x dot shape, I get told that the shape of x is just 5. That is, x is a one-dimensional endy array containing 5 items. And if I say x.dtype, I get told that it contains int32s. And if I say x.endim, I get told that the number of dimensions of x is 1. A Pandas series similarly has various attributes, and one of these is index, which by default are these values 0 through 4. And in fact, within the Pandas library, there's a data type called range index, which is very similar to the range function. And so the range index here is starting from 0, going up to but not including 5 with a step size of 1. I also have v2.values, which is the values contained within the series. So if I would like to get that endy array out, I can just say x2 in this case is v2.values. So now x is an endy array, x2 is also an endy array. If I compare whether x is equal to x2, unlike a list equality comparison where I simply get a true or false, in this case, because x and x2 are endy arrays, they get compared on an item-by-item basis. And so what I'm going to end up with is an endy array of 5 true values, okay? Because 5 does equal 5, 9 does equal 9, 10 does equal 10, and so forth. Okay, so notice in both of these examples, the one on the left in which we used a list of integer values to provide the data for our series, and the one on the right where we used, pardon me, where we used an array, where we used an endy array, excuse me, to provide the initial values for the series. In both cases, we didn't specify that we wanted any particular kind of index, and consequently what we got by default was these ascending integer values 0 through 4 in both cases. It is possible to specify the index that you want by using the index keyword parameter in the series creation function. So here in creating v3, I'm going to use the same data. Let me just remind ourselves what data contains. So data is a list. I'm going to use the same data to provide the initial values. But this time I'm going to create my own index rather than using the default. And the index is going to be a list provided by a list of just these letters A, B, C, D, E. Okay, all right, so there we are. So this time I'm choosing to use one character strings, A, B, C, D, E, as my index rather than the default integer values 0 through 5. And when I display v3, I see that, yes, I have these labels A, B, C, D, E. If I ask to see the values of v3, remember that values is a property of the series. I can also ask to see the index of the series. And so I can see the index that way. An alternative way of creating a series with both the indexes and the corresponding values specified is to construct the series from a dictionary. Now, in the dictionary, we always have a key, and then if we create a dictionary from scratch on the at the shell line or in our code, the notation is we say D gets and then curly braces with key colon value pairs. So let me create this dictionary here. D gets. Okay, the key is going to be 7, and the value associated with that key of 7 is dog. Then I've got the key 10 with Hyrax as the value, and finally the key 3 with gopher as the value. All right, so now I have a dictionary, and as a special case, the series creation function knows how to take a dictionary as its argument and pull the keys out to use those as the index values and the values out to use those as the values corresponding to the index. So v4 here now has the keys 7, 10, and 3, and notice that they are in that order. They are in the order specified with the values dog, Hyrax, and gopher. So I can ask for v4.index to see the index values, and I can ask for v4.values to see the values, and I can take the contents of that series back into a dictionary by saying v4.toDict. And notice, just to be annoying, somebody wasn't thinking when they developed this part of Pandas. ToDict requires an underscore between the to and the dict. ToList, on the other hand, requires that you don't have an underscore. So if I say ToList, I don't use an underscore in the name, which is sort of, it's inconsistent and therefore annoying and hard to remember. But anyway, D2 here is a dictionary equivalent to, or equal in content to D that I created my series from. And M is just the values. The indexes are lost when we convert a dictionary to a list. Okay, now you can use the in operator just as you can with a set or a dictionary to determine whether a particular index is found in a series. All right, so here I have V4, and I can say, I can ask whether 7 is in V4. And that's true because 7 is a key. I can ask whether 12 is in V4, and that's false because 12 is not an index in V4. I can ask whether dog is in V4, and this may surprise you. This is false because dog is one of the values in the series. Dog is not one of the indices. It's not an index in the series. Actually, this is the same as what we saw when we were working directly with dictionaries themselves. Did I say dictionary just a minute? I meant to say dog is not an index. Yeah, I think I said it right. Dog is not an index in the series V4. Likewise, dog is not a key in the dict D2, so that is false for the same reason. We can use slicing on a series, and that will treat the initial item in the series as being item sub 0, and so on. So if I say V4 sub 7, this will get me back dog. In slice, if I say V4 sub 0, that's an error because there is no index 0 in V4. However, in slice notation, I can say V4 sub 0 colon 2, and in slice notation, this will be recognized as meaning give me the items from item sub 0 up to but not including item sub 2, and what I get are the first two items, dog and hyrax, in the series. So likewise, V4 colon 2 is the same thing. Okay, the missing initial index is interpreted to be 0 by default. Okay. Well, just as you can read from a comma-separated value file to create a NumPy ND array, you can also read from a comma-separated value file to create a data frame. Although in NumPy, you would say gen from text, and then you'd have to specify the delimiter as a parameter. Here, there's a special individual function, readCSV, that knows specifically how to interpret comma-separated value files. And you can indicate that one of the columns in the comma-separated value file should be used as the index rather than as values. Okay, so let me whack together this mydata.csv file, and then we'll demonstrate how this function works. So I'm going to come back to you in a moment. All right, so here I have created this mydata.csv file, and each line in the CSV file has two columns. The first column is a string, the second column is a number. And I want to use those strings as my indexes and the integers as values. Okay, so I can say, let me scoot this over. Well, I'm covering what I want to talk about. Let me slide this up. All right, so now let me say v15 gets pd.readCSV, and the first thing I'm going to give is my name, is the name of the file, mydata.csv. And the second thing I'm going to say is that I want the index column to be the sub-0 column, the initial column in the file. Whoopsie, I apparently am not in the correct directory. So let me type in the whole path name of this file. Okay, so this is going to be c:/users/jostlin/ and then the name of my directory for our course is okay, so the place where I have my course files here is this directory 90819 A3 2022. And now let me read in the data.csv file with column sub-0 as my index. No. Almost, but let me... I forgot to call it my data, so let me copy and paste the directory name. And we'll finally get this to work. Yay! So now you can see that I've got... Oh, now interesting, I had forgotten this. It treats the first row as column names, which isn't what I wanted. So we would also have to fuss around figuring out how to avoid that. All right, I don't think I want to flog this to death. If you look at the documentation for read CSV, you'll discover that it has an oodle of keyword arguments that you can use to specify the index column, the header row, on and on. But we've got a series called V, and let's take a look now at doing some arithmetic with a series. You can do scalar arithmetic with numeric series, numeric data, Pandas series, basically in the same way that you can do it with one-dimensional ND arrays. So here's my series V. If I say V times 3, each of the item values, 5, 9, 10, 12, and 20, 10, 2, and 12, will get multiplied by 3. But notice that the index values don't change. Likewise, if I say V over 2, that is going to do a division. Now, division always results in a float value. Notice that the values in this series, V over 2, are of type float64 rather than int. I want to be clear that neither of these arithmetic operations is modifying V. Instead, they're simply making a copy of V, multiplying that copy by 3 or dividing that copy by 2, and then displaying a copy of the resulting series. So if I were to, so here's my V. If I were to say V by 2 gets V over 2, now I would have a variable referring to that modified series. Okay, it's an entirely separate series from V. In fact, I can confirm that the ID of V is different from the ID of V by 2. All right. It's possible that I didn't talk about the ID function yet, so let me just do that now. All objects in memory in Python are designated by a unique ID number. And you can display the ID number by using the ID function. Here I'm displaying the IDs of V and V by 2, And because those values are not the same, that means that the two objects are not the same. If I say W gets V, well, now V looks like this, W looks like this. Actually, W is just referring to the same object as V. So if I ask for the ID of V, I get some number. And if I ask for the ID of W, well, W is just a different reference to that same object, and so it has the same ID. Okay, and then I can also do addition, subtraction. I can treat series, as long as there's the same dimension, as vectors. And what actually matters is that they have to have the same indexes. So I already have this vector called V that has indexes 0 through 4 with these values 5, 9, 10, 12, 5, 9, 10, 2, 12. I'm going to create this new series V5, and it is going to be created from this list. I'm using comprehension here. I times I for I in range 5. Whoop, forgot my closing square bracket. So V5 now contains the squares of the integers from 0 up to 4. And the indexes are the same. So because the indexes are the same and the sizes are the same, if I add these together, V plus V5, I get what I would probably expect. 5 plus 0 is 5, 9 plus 1 is 10, 10 plus 4 is 14, and so on. Okay, and so there is my vector sum. However, if the indexes between the two vectors that you're adding do not match, then you run into a problem. So here is V, and I'm going to create a new series V6. PD.series. I'm going to create it containing the same values. So I should have been smart enough to copy and paste for I in range 5. But I'm going to use a different index. I'm going to specify an index of I for I in range 2, 7. Now 2, 7, again, I'm using a comprehension here. 2, 7 means to specify index values from 2 up to but not including 7. So my indexes for V are 0, 1, 2, 3, 4. My indexes for V6 are going to be 2, 3, 4, 5, 6. And now, even though V and V6 both have 5 items in them, when I add them together, it's the indexes that decide what gets added to what. V has indexes 0 and 1, but there's no corresponding indexes 0 and 1 in V6. Likewise, V6 has indexes 5 and 6, but there are no corresponding indexes 5 and 6 in V. So the only things that are going to successfully get added here are the 10 with index 2 in V is going to be added to the 0 with index 2 in V6. 2 is going to be added to 1. 12 is going to be added to 4. And for all the indexes where a value exists in one but not the other, what I end up with are these not a number indications, okay? So I added, in this case, a value in V that doesn't have a corresponding value in V6, and that produces not a number. Okay, so I've got 2 values in V6 with indexes 0 and 1 with no corresponding indexes in V6, so I get not a numbers. And then the same thing happens for the 2 indexes 5 and 6 in V6. I get not a numbers. Now, sometimes this happens. You have two different data sets. Maybe people's names are the indexes, and I don't know, their incomes are the values. Okay, so their dollar incomes for 1 year and dollar incomes for another year are the values of those two series, of those two data sets. Well, when I add those things together, what I'm interested in is finding out what the total salary is that these people made over 2 years. But I may have certain people in my first list, in my first series, that don't exist in my second series, and similarly, certain people in my second series that don't exist in my first. So how can I figure out and obtain just those people that are common to both? It turns out that I can use an Is-Null test to test whether I have nada numbers, or a not-null test to test whether I don't have nada numbers on an individual basis. Let me create V7 here as the sum of V plus V6. So here's V7. And if I now ask for V7 dot Is-Null, I'm going to get trues for all the nada numbers and falses for the numbers. On the other hand, if I say V7 dot not null, I get true for the numbers and false for the nada numbers. What can I do with that? Well, it turns out that I can use this V7 dot not null as what a so-called Boolean index into my series. I can use the not null as an index into my series to extract from the series only those values that have actual numbers. So here I'm saying V8 gets from V7 all of the rows from V7 where the values are not null. Okay, so V8 now only has 3 items in it, and those items are the ones where V7 dot not null was true. Now, as we said before, when we created an index of A, B, C, D, E, we don't have to have integers for our index. Here we're using the index Ohio, New York, Michigan. And let me quickly create this V9 vector. So V9 is our pd.series. The values I'm going to provide from the range function, range 3. Okay. We used lists to provide data. We used ND arrays to provide data. We used a dictionary to provide data. Here I'm using the range function, and recall that the range function is an iterable that's going to produce the integer values 0, 1, 2 in this case. So range is yet another way of providing data for a series. And my index, I'm going to type my index on the next line because I'm going to run out of space, is going to be... All right, well, I'm too lazy to type entire state names, so I'm going to type their 2-letter codes. Okay, so there is V9 with my keys, Ohio, New York, Michigan, and values 0, 1, 2. I can just see the index, of course, by saying v9.index. There we are. I can see the values by saying v9.values. There we are. Oh, here I see. Okay, here in this on this slide, we've said I gets v9.index. So later on, when we just display I, we get the index. Okay. Okay, you can create a new series by using a copy of some other series index. Here we're saying index gets I, and that is the I from back here. I don't actually need to use that variable I, though. I can just say v10 gets pd dot series 100 minus 5 minus 2 as my data, and I can say index gets v9 dot index. All right, v9 dot index is what we saw here, and I can just use that index as the index to be used to create v10. And so now v10 has the same indexes in the same order, Ohio, New York, Michigan, with the specified values. Now, I can use the index to access individual values within the series. So v10 sub New York, NY in my case, gives me the value for the index NY. It turns out also, and this is not so necessary for single-dimensional series, but I can use the loc method. I can say v10.loc, and square bracket ny, as a somewhat more long-winded way of specifying that I want to access the ny index. Now, as an alternative to loc, let's suppose I did want to use my integer subscripts, 0, 1, and 2, to access the items within this series. Then I can use something called iloc, the integer location of a particular value. So iloc 1, that's going to be the sub 1 item within the series. It's going to be the same thing as the one that has the index of ny. Okay? And I can do slicing by remembering to use iloc. So that's going to give me New York and Michigan, the slice from item sub 1 to the end. Okay? Now, so here we have some confusion. So indexes are used to, the index is used to provide basically the subscripts or the indexes for the items in a series, and you can display the indexes. If I say, or you can display things from the index. So if I say v9.index sub 1, all right, remember that v9.index is the index for v9, and I can access those items using ordinary integer subscripts. So v9 dot index sub 0 is Ohio, and so on. I can ask for slices. v9.index sub colon 2 means 0 and 1. But the index is immutable. That is, if I try to say v9.index sub 2 gets Idaho. Okay, I know the example here is Indiana. Well, I guess I'll use Indiana to be consistent. All right, so if I try to change the index for Michigan to Indiana, I get yelled at. Okay, does not support mutable operations. So the index is immutable. However, I don't know if this is a however or not. You can rename an index using this sort of odd dictionary notation. Here's my good old original series V. And V has the integer indexes 0, 1, 2, 3, 4. If I say V dot rename, okay, I can specify a change of 0 to 52. And now I have this series with 0, the index 0, replaced with the index 52. But I want to be careful here. This is not actually modifying V's index. V's index has not changed. What v.rename does is to return to me a new series in which the index 0 was renamed as 52. So I could say VA, let's say, is v.rename the 0 to 52. And I did that wrong. All right, so So V is unchanged. VA, on the other hand, is a copy of V in which the first index has been changed to 52. Well, actually, though, if I don't want to get a copy of V with one of the indexes renamed, there's another keyword argument that I can use, a keyword parameter called in place, which violates the immutability of the indexes. So here's V. If I now say V dot rename the index 0 to 52, but do this in place by setting in place to true, well, now I have changed the index within V itself of the first item from 0 to 52. So what does immutable mean in this case? Well, immutable means that it's a little bit difficult to do, all right? But you can, if you use rename with the in place keyword argument, you can force it to happen. So, yeah, sometimes immutability is real immutability. In this case, it's challenging immutability, but you can still force it to happen. Alrighty. You can also have duplicate indexes, but this is frankly a dumb thing to do, and it usually is going to lead to mistakes either on your part or on... Well, I won't say that Pandas makes mistakes, but sometimes Pandas will do things that you don't expect if you are foolish enough to create indexes that match. So here I'm going to create a series with strings as my values: dog, cat, and gopher. And I'm going to establish an index of integer values, but this time both of the first two index values are going to be 5. All right, now let's think about this. You can do this in a spreadsheet, and Pandas, in some sense, is sort of simulating in Python the kinds of operations you can do in a spreadsheet. You could create a spreadsheet that has the same person's name appearing in column sub 0 multiple times, and think of the person's name as your index. Now, in reality, having having a given person's name appear multiple times in a given column of of a spreadsheet is likely to lead to problems, and the same thing is true here. So if I ask for V11 index duplicated, I will get whether a given index has is a duplicate of some other index. And this output of the duplicated function is in the same order as the records in the series. So when we analyze the first record, we've never seen 5 before, so we say, well, that index is not duplicated. But when we then analyze the second record, we see 5 again, and we say, oh, that index is duplicated. And then we get down to the third record, and we say, nope, 3 is not duplicated. So we've identified the second record here as having a duplicated index. And it turns out, and this is a logical operation. You can take a series such as duplicated here, and you can say that you want to invert all the false values to true and all the true values to false by using this tilde symbol. This is borrowed from the C language. The tilde symbol in the C language means to invert all of the zeros to ones and all of the ones to zeros in the bit pattern for some integer. And here the meaning has been extended to convert all Boolean values to their opposites, or invert all Boolean values to their opposites. So here I have true, false, true as the inversion of false, true, false. And I can use this Boolean index within V11 to say, all right, I want to change V11 to contain just those items where the index is not duplicated. So V11 now contains 5 with dog and 3 with gopher. All right, because 5 was the first non-duplicated index. The 5 for cat was duplicated, so cat is left out. All right, now it's also possible to provide a keyword argument to the duplicated function to indicate whether you do want to keep the first version that's duplicated or the last version that's duplicated. Let me show that. So here I have v11.index.duplicated. Whoops. I've changed v11. I want to get v11 back. So let me get v11 back to what it was initially. All right, here's what v11 was initially. And if I say v11.index.duplicated, this is equivalent to saying keep equals first. Okay, so keep equals first is the default, and so I'm going to keep the first instance of any duplicated indexes. But as an alternative, I can say keep equals last. And this time, I'm going to keep cat, okay, because cat is the last instance of the index 5. And of course, I can invert this thing by sticking a tilde in front of it. And then I can use that as my Boolean index to suck out just a certain part. I don't want to change V11 again, but let me just access from within V11 the records where we keep the last occurrence of each duplicated index. So now I'm keeping cat and gopher as opposed to dog and gopher. Now, the reindex function allows you to change the order of indexes and also allows you to add new indexes. Those new indexes will have no values. That is, they'll have the equivalent of an empty value for the for whatever value is missing. We haven't seen V10 for a while, so here's V10. V10 contains the indexes Ohio, New York, Michigan, with these integer values 100, minus 5, minus 2. If I say v10.reindex, and I give, and again, I'm going to be lazy, I give IA and NY and MI and OH as my changed indexes, my reindexed indexes, that returns to me, whoops, I made a mistake. I typed NI instead of MI, so let me try that again. All right, here's V10, and now here is a reindexed copy of V10. V10 itself is not being changed. I'm getting back a reindexed copy. The original order of the indexes was Ohio, New York, Michigan. The order of the reindexed series is Iowa, New York, Michigan, Ohio. And notice that for the pre-existing indexes, NY, MI, and OH, the values have been preserved. Okay, so minus 5 for New York, minus 2 for Michigan, 100 for Ohio. Although for some strange reason, and I don't know why this is, the data types. Oh, I know why this is. Of course, I know why this is. Iowa did not exist, IA. So we got not a number for IA. And not a number, it turns out, even though it's not a number, is represented as a floating point value in float64 type. And because Iowa's value has data type not float64, the other ones are getting converted to float64 as well. Okay? Now, here's V11. It turns out that I cannot do a reindex if I have duplicate values in my reindexing. So my hope here by reindexing V11 is that I'll now have index 5 and then 3 and then a new index 7 and then 5. But because I've got 5 twice in my series, Pandas has no way of figuring out, well, okay, so which 5 is this first 5, which 5 is the second 5, and so Pandas just throws up its hands and says, I don't know what to do here. Okay, cannot reindex. Another way, whoops, I guess I didn't create V12. Well, that's all right. I've got V11. No, I've got V... What did I create? What did I create? Did I create V12? No, I didn't create V12, but I do have V10. And let me go back and repeat the reindexing and create for myself this V12. Sorry about that. All right, so I'm going to create V12 to be the reindexed V10. So there's V12. Now, we have talked about two different notations for getting values out of this series. One way is I can say v12.loc and then specify an index. And that gets me the value associated with that particular index. As an abbreviation, I can just use the square brackets directly, and that means the same thing. But if I want to obtain that value in terms of the integer ordering of the indexes, I can use iloc to ask for item sub 0. Okay, so I can use both names as indexes and I can use integers as indexes. It turns out I can also use a list of indexes to access, not only access indexes, but also change their orders. So if I say v12 sub and then sub IA, well, this is going to appear to be redundant, all right? However, notice that it's returning to me an entire series containing just Iowa as opposed to returning to me the value associated with Iowa. The cool thing here is I can ask for multiple indexes. So let me ask for New York and Ohio and Iowa. And what I'm going to get back is an entire series just containing the records for New York, Ohio, and Iowa, and they will be in that order. So the ordering of the indexes now is going to be New York, Ohio, and Iowa. Okay. Whoop. Finally, if I want to get rid of one of these records, I can use the drop function. So here is my v12. And if I see v12.drop Ohio, then I'm going to get back a copy of that series with Ohio dropped. v12 itself is not modified. But I can do this in place, as we talked about previously with the reindexing. If I say v12.drop Ohio in place is true, then this does not return a modified copy. Instead, it does the modification directly in place. So my record describing Ohio is now gone. Okay, so that gets us to the conclusion of our first round of discussion about pandas. In this material, we talked about the series data type, and in the next lecture, we'll talk about the data frame data type, which extends this out to having multiple columns instead of just one column of values.